Assalamualaikum and good evening. We are from Group 3. We'll present the experiment 6, which is the torsion of bar. And these are our group members. The torsion bar is a flexible spring that can be moved around its axis by twisting. It can be designed based on the torque amount used, the torsion angle, the size of torsion bar, and its material. A torsion bar works by counteracting the torque placed on it. When one end of the torsion bar attached to a fixed clamp, the other end of the rod is twisted that can form a torque. When this happens, the torsion bar will stand the torque and will return to its original position after removing the torque. Torque is the measure of the force that can cause an object to rotate about an axis. Two types of torque are static and dynamic. Static torque doesn't produce any angular acceleration, while dynamic will produce it. The example for static torque is a pushing a closed door, where the reactive force was produced but there is no rotating motion occur. The torsion of bar experiment was the example of dynamic torque. The diagram shows the formula of torque, which is torque equal to Fr sin theta, where F stands for force, R for distance, and theta for the angular between the force and lever arm. The objective of this experiment is to investigate the relationship between torque and the angle of twist of a circular rod and to determine the modulus of rigidity of the materials. There are three scopes for this experiment. The first one is the coverage of this study is the different material of rod used, which are nylon, aluminium, and steel. Second, the study consists of two different lengths of rotation scale and the pointer from the fixed clamp, which are from 200 mm and 240 mm. Third, the study covers the range weight of the load within 5 to 40 Newton. Due to limitation of the equipment, the weight of load applied at nylon rod is between 0 to 5 Newton because the angle of the twist is more than 90 degrees for nylon.
Next, I will talk about the theory behind this experiment. When we talk about torsion of bar, there are a variety of cross-section of shaft that involves. There are two main cross-sectional shape, circular cross-section and square cross-section. When a circular shaft is subjected to torsion, every cross-section remains plane and undistorted. In other words, while the various cross-sections along the shaft rotate through different amounts, each cross-section rotates as a solid rigid layer. When a bar of square cross-section is subjected to torsion, its various cross-sections warp and do not remain plane. The cross-sections of a circular shaft remain plane and undistorted because a circular shaft is axis symmetric. Its appearance remains the same when it is viewed from a fixed position and rotated about its axis through an arbitrary angle. Square bars, on the other hand, retain the same appearance only if they are rotated through 90 degrees or 180 degrees. When a rod is attached to the torsion bar, the original position of rod will be at AB. When a shear stress is applied on torsion bar, the rod will deform by twisting. The rotation and deformation will stop at some fixed strain angle, which is called angle of twist. When a constant shear force is applied, the rod will move to a new position labeled as B prime. In order to know to what extent the rod will deform, we will calculate shear strain using the formula shear strain equals to product of distance from center of cross-sectional to any point in the rod and angle of twist divided by length of rod. Then we can calculate torque using the formula force times radius of torsion head. Polar moment of inertia, also known as second polar moment of area, is cross-section's resistance to torsion due to rod shape. The higher the polar moment of inertia, the larger the torsional resistance of the object. Can be calculated using the formula polar moment of inertia equals to pi r power of 4 divided by 2. According to Hooke's law, stress is directly proportional to strain within the elastic limit of that solid. Since the shearing stress and strain did not exist anywhere in the rod, so we calculate modulus of rigidity G to give us value to what extent the deformation might occur. The G will be calculated using the formula torque times length of rod between fixed clamp and rotational scale divided by angle of twist and polar moment of inertia. As long as the yield strength proportional limit is not exceeded in any part of a circular shaft. When the length of rod between fixed clamp and rotational scale increase, the angle of twist increases and torque increases. Modulus of rigidity is inversely proportional to angle of twist but proportional to the torque. So this is what we're supposed to get theoretically. The theoretical value for modulus of rigidity for material that we investigate in this experiment is aluminium is 26,000, steel is 75,000, and nylon is 3,933 Newton per millimeter square.
Experiment setup. So for our experiment setup, here we are using torsion bar testing machine. There are three main components. There is rotation scale, a pulley, and a fixed clamp. So the apparatus that we are going to use are rods that are three types: nylon, aluminium, and steel. Then we have measuring tape, a key lock, a ruler, a vernier caliper. Load varies from 1 Newton to 5 Newton, a hanger load that count as 1 Newton. So for the methodology, so the step 1, measure the length of each rod, nylon, aluminum, steel using the measuring tape, and also measure the outer diameter of each rod using vernier caliper. So the step 2 is the rotation scale will be set to a distance of 200 millimeter from the fixed clamp. Step 3 is to insert the nylon rod into the clamp. And then step 4 is when locking the clamp, a person should hold the string of the pulley, while another person should lock the clamp tightly with the key lock, and make sure the clamp will be tight, very tight, to ensure the full capabilities of the rotation of the rod. Step 5 is the plastic cord on the rod will be set to 0 degrees on the rotation scale. So the step 6 is to add load of 1 Newton to the load hanger. For step 7, read and record the data that are measured on the rotation scale. And step 8 is to repeat step 7 until 8 with different loads: 2 Newton, 3 Newton, 4 Newton, and 5 Newton for only nylon rod. So step 9 is to read and record the data that are measured on the rotation scale. Step 10 is to repeat step 4 to 9, but the rotation scale will be set to a distance of 240 millimeter from the fixed clamp. And lastly, then step 11 is to repeat step 2 to 10 with different types of rods, aluminum steel, but this time the load will be heavier. That is 5 Newton, 10 Newton, 15 Newton, 20 Newton, and 25 Newton. Due to the nylon, we use lighter load because due to the limitations of the rotation scale. Next will be the result and discussion.
Result and discussion. First, torsion head effective diameter is recorded and divided by 2 to get radius. Table 1 shows the result of aluminium. At Table 1, the first column shows the weight used. The second column shows the angle of twist obtained in degree over 200 mm and over 240 mm, where the third column shows torque calculated. The last column shows angle of twist in radian unit. By converting degree to radian, we multiply pi over 180 degree. An example calculation of torque using aluminum rod shows at below Table 1. Torque equals to force applied times radius of torsion head effective. Next, graph of angle of twist in radian angle against torque is plotted. The gradient m is obtained from the graph plotted. Polar movement of initial j equals to pi r power of 4 over 2. The R is the radius of aluminum rod. Modulus rigidity is TL over phi j, where the gradient obtained is phi over T. Therefore, by substituting the gradient inside the modulus of rigidity, we will get modulus of rigidity equals to L over Jm. Modulus rigidity is the average modulus rigidity at 200 millimeter and 240 millimeter. Next, this is calculation for steel rod and nylon rod. Calculation modulus of rigidity for steel rod and nylon rod is using same method as calculation modulus of rigidity for aluminum rod. Through experimental conducted, angle of twist increases, the torque increases. Based on the three graph plotted, graph shows the angle of twist is directly proportional to the torque for each material, which is aluminum rod, steel rod, and nylon rod respectively. Secondly, angle of twist is also affected by length of rod between fixed clamp and rotational scale. Through experimental conducted, the longer the length of rod between fixed clamp and rotational scale, the greater the angle of twist. Graph shows an angle of twist is directly proportional to the length of each rod between fixed clamp and rotational scale, which is aluminum rod, steel rod, nylon rod respectively, with two different values of length 200 mm and 240 mm. Next, graph shows angle of twist is inversely proportional to the modulus of rigidity. The greater the angle of twist, the lower the modulus of rigidity. Experimental value of the modulus rigidity of aluminum rod is 21498.68 Newton per millimeter squared. Steel rod is 60389.57 Newton per millimeter squared. And nylon rod is 2371.41 Newton per millimeter squared. Hence, the modulus rigidity in ascending order is nylon rod, followed by aluminum rod and steel rod. Therefore, the highest angle of twist is nylon rod, followed by aluminum rod and steel rod. In conclusion, the torque twist formula is verified to be true based on the graph plotted. G equals to TL over phi j, where the phi is angle of twist, T is torque, L is length of rod between fixed clamp and rotational scale, J is polar moment of inertia, G is modulus of rigidity. As the length of rotational scale and pointer from the fixed clamp increases, angle of twist of rod increases. This can be proved by the experiment conducted. The angle of twist rod at 240 mm length of rotational scale and pointer from the fixed clamp is larger than that at 200 mm. Within our investigated range, all the rods exhibit elastic behavior. As long as the force or torque exerted did not exceed the maximum limit, the rod can return to its original position and will not deform permanently. Angle of twist of aluminum is higher than steel but lower than nylon because aluminum is more ductile than steel. To find out how much of our experimental value deviate from theoretical value, we using the percentage of deviation as our formula. Table 4 shows the percentage of deviation between experimental modulus of rigidity with its theoretical value. From Table 4, there are slightly differences between experimental and theoretical modulus of rigidity, which are in the range of 20.94% to 65.85%. The difference of experimental values from the theoretical value is due to some errors that occur during the experiment. The error which might have occurred include First, parallax error. Readings were taken when eyes are not positioned perpendicular to the measurement marking, which cause inaccurate reading at the angle of twist on the rotational scale. Length of rod between fixed clamp and rotational scale on the measuring tab, and diameter of each rod on the vernier caliper. Second, random error. Environmental factor due to the air movements in the lab will cause the rod hanger to swing, which lead to inaccurate reading of angle of twist on the rotational scale. The experiment proved the theory that when G equals to TL over phi J, torque increases, modulus of rigidity increases. Length of rod between fixed clamp and rotational scale increases, modulus of rigidity increases. Angle of twist decreases, modulus of rigidity increases. Polar moment of inertia decreases, modulus of rigidity increases. Through experiment, the highest modulus of rigidity is steel rod, followed by aluminum rod, and the lowest modulus of rigidity is nylon rod. This is because steel is alloy where the material is composed of two or more metallic elements. Aluminum is pure metal where the material is composed of one type of metal. Nylon is polymer where the material is organic compound that chemically based on carbon, oxygen, nitrogen, hydrogen, and other non-metallic elements. Alloy have higher mechanical strength than pure metal because presence of atoms of different sizes that disturb the orderly arrangement of atoms in alloy. This reduces the layer of atoms from sliding each other. Metal have orderly arrangement of atoms. Thus, the layer of atoms can easily slide over each other, making pure metal less stronger than alloy. While polymer has the lowest mechanical strength compared to alloy and pure metal. This is because polymer has weaker intermolecular bonds, which is weak van der Waals force, but metal has stronger metallic bond. Therefore, change of polymer can more easily make in less ductile than metal.
For the conclusion, as a conclusion, experiment is aimed to investigate the relationship between torque and the angle of twist, as well as the materials modulus of rigidity. The three materials that was used to investigate is aluminum, steel, and nylon rod. It is evident from the plotted graph that torque was directly proportional to twist angle for all three materials. Angle of twist is inversely proportional to the modulus of rigidity. From the experiment, the modulus of rigidity we obtain is still has the highest volume, followed by aluminum rod, and the lowest modulus of rigidity is nylon rod. For possible error, we have parallax error, and the equipment have their own limitation. For the improvement, the observer must keep his eye or her eye level perpendicular to the scale of the measuring devices at all times. Collect multiple sets of reading in order to acquire an average reading. Make sure the rod is tightly clamped to ensure the full capabilities of the rotation of the rod. For safety and precaution, for the laboratory safety, first, wear appropriate personal protective equipment, including lab coats, gloves, and closed-toe shoes to protect against hazardous material like heavy weight might fall on our foot or corrosive material that might harm our skin. Tie back long hair and avoid wearing loose clothing and jewelry that could cause in equipment. For precaution steps, take the measurement reading with your eyes perpendicular to the rotation scale to minimize parallax error. Apply loads gradually and within the specified limits to prevent the equipment from being damaged. Conduct the experiment carefully to prevent any errors and injury. Next, for the references, this is the reference that we study to make our report. That's all from us. Thank you.